Geometric representation and the arithmetic of complex numbers. Almost have a palindrome date. Almost. Not quite. Okay, so we're going to look at the addition of vectors first. So in all these examples, let A equal, 4 plus 2y. And B is going to be 1 plus 4y. Okay? So the vector OC, okay, so the endpoint, the result of that is the addition of the vectors of OA and OB. Okay, so OC, that way is going to be OA. Have you done the arrows on tops? Hey? Only in physics, but you know what they mean? Yes, good. Okay, so obviously we're starting at the first letter and finishing at the second letter. Okay, so we can move the vector OB. Okay, so we can translate that vector OB to the tail, the head, of the vector OA. Or we can translate the vector OA onto the head of the vector OB. Okay, so either way, we put the, hey?
It's where the lines, where CA is.
So I want to add this vector and that vector, so I move this vector onto the head of this vector, and the resultant vector is that. Or I can move this vector onto the tail of that vector, and I'll end up at the same point. Okay, so addition you can do just like in arithmetic, 3 plus 4, same as 4 plus 3. If you want to do addition to vectors, we can add them in any order we want. Okay, so we simply translate the tail of one of the vectors onto the head of the other, and the result will be over at C. Okay, subtraction. Alright, so O, A and B, so the same point A and B. So when we do a subtraction, you know you need to reverse the second vector, direction of the second vector, and then put that onto the head of the first vector. Alright, so this is A take away B. So the negative B means you swap in the reverse order down here. Okay, and then once you swap, you then translate that to the tail OA. Okay, or in other words, you put the tail on the opposite end, and then you translate that to the head of the first vector. Okay, and that's how you do a subtraction. Either way, you'll get the same point. Alright, multiplication. Okay, so we've already looked in the multiplication and division of vectors in modulus argument form. Okay, so we've got the distance OA and OB. Okay, so there's now different values of A and B in there. Okay, so here I've set up a GeoGebra file. The distance OA is 2.83 and the distance OB is 2. Alright, so when I multiply, okay, I multiply the distance of both the vectors. So 2.83 times 2 is approximately 5.66, and that 2.83 is also approximate. And we add the argument. Okay, so the angle makes with the vector at A, so this angle here is 45 degrees. Okay, and because it's 2, 2. And that second angle with vector B, that's 30 degrees. Alright, and when you add them together, you'll get 75 degrees. Alright, when you're multiplying in vector form. Alright, so the same principles of what we just covered. Alright, division. Right, So A and B are the same points as before. So the angle A is 40, the angle to the vector OA is 45 degrees, and the angle to vector B is 30 degrees. Okay, so 45 take away 30. Okay, so that means that middle angle is 15 degrees. And the distance of the vectors, so 2.83 approximate, and 2, you do a division, so 2.83 divided by 2, 1.41. Coincidentally, the square root of 2. Or is it a coincidence? Probably not. Okay, so that's how we do. So we just covered multiplication and division. Right, that's what it looks like in vector form. Yep. Alright. Examples. A is that and B is that. Compute C and label the vector OC for each of those 4 variables to C onto the argument diagram. Okay, I've done 20. It's your turn. Right, so addition and subtraction. Right, we don't need to do anything in terms of modulus argument for that. Same when you do the multiplication and division. We need to represent those in modulus argument form. Right, I reckon I'll give you 5 minutes and you'll have more drawn. Okay, so there's 2 complex numbers. So label OC 1, 2, 3 and 4 onto your argument diagrams. So first you need to do the addition of 2 complex numbers and the subtraction, watching your order. B take away A, not A take away B, which will result in a different vector. Right, C1 is going to be negative 4 plus 4i plus 3 plus 3 root 3i. This is simple. This is the easy stuff. Days, haven't they? The planes have been around a lot the last couple of days. in 3 root 3. Plus 9, 36, 18 twos. Plus 9 root 2, 4 root 2. Root 2 times root 2, 9 eighths and 972. Four pi and 3 pi, 6, 7 pi on 12. C4, A over B. So 9 take away 4. A 25. Alright, so C1. I'm going to have to approximate that. Source 4 plus 3 root 3. Approximately. C1.
10.
Oh, about that.
12.
Can you give me a bit more?
11.5.
Can you get one of you get your calculators out? And get 4 plus 3 root 3 for me, please. I think it's about 10, yeah.
I'm going to say 11.5. 9.1961.
So almost 9. Just over 9. So needy 1 plus 9i approximately. Okay. So that's C1. That's of course our origin. So we're labelling the vector C1. From the origin, C2, 3 root 3 take away 4. So 3 root 3 plus 4, so 3 root 3 just over 5. So we've got 5 over 4, so we've got something just over 1. 7 plus 1. So 7. Now I'm drawing really small because we've got a 72 to deal with here. So I'm just trying to keep things in proportion. Alright, so 7 pi on 12. Pi on 12 is, we've seen 2 or 3 questions already with pi on 12. 15, 7 times 15. Okay, so where would 105 be? Yep, 15 degrees further. At a radius of 72. So we're way up here somewhere. Okay, you should probably, right, so you will be using the rules. I'm not being a good example. Okay, so C3 is somewhere way up there. And C4, so what is 5 pi and 4?
225.
220, we were saying that one before as well, haven't we? At 904, so 2. Yep. Okay, so we probably could have drawn the vectors A and B in there to begin with. Okay, and then used what we just learnt. Okay, but we still had to work out the modulus argument form, etc., etc. Anyway, so that's what they're looking for these questions.